All right, we're going to go ahead and get started. I want to start the class with some stuff about some logistics, as well as sort of to address some questions that have come up on Piazza about the grades on the midterm, and some people have concerns about what that might mean for their grades on the final class. It was interesting to go back and compare the means and the distributions on the midterm last year. It's near identical. So last year the mean was about 69%. This year it was about 71%. And you see pretty similar distributions. The one on the top is the one on the bottom is ours. So you can see this is 2019, this is 2018. So they look pretty similar distributions. We don't do an official curve for the class. If anybody's getting over 90%, I always consider, even if everybody gets over 90%, that means that those people all understand the material well enough to deserve an A. And then if we have really abnormal distributions, then sometimes we curve below that. But just to give you a sense, last year about 42% of people got an A in the class. So for those of you that are concerned about your midterm performance and concerned about your final grade and whether it's still possible to do well in the class, it definitely is. So does anybody have any questions about the midterm? I know we've had some regrade requests, and we're going through those as quickly as we can. Yeah.
Is there any, this is probably like very out of curiosity, but is there any distribution available per question? Because I feel like, for example, for me, I just ran out of time on the last questions, and I wonder if that's...
We have that information. I'll double check with the CAs that there's no reason we shouldn't release that. I don't think there is. So GradeScope gives us full distributions for all of the questions. So we can release that. A lot of people ran out of time. The last problem was definitely the hardest. So that was where we saw the biggest variation. And so that's where we tried to be particularly careful on the rubric. And we very much tried to make sure that if you're doing algebraic mistakes throughout the exam, that was worth very little, and we were focusing on the conceptual understanding. Any other questions about the midterm? So I'll just write down per problem breakdown. Basically, when we're going through it, we tried to look at any problem that had really high variance and then step through the rubric again to make sure that we were being fair. Oh, one other thing, which is we're going to continue to accept regrade requests for the midterm through Friday. And after that, it'll be closed. Okay, so that's the midterm. Hopefully that helps sort of quell some concerns from at least some of people in the class. The other thing that I wanted to bring up right now is the quiz. So the quiz is going to be in about 2 weeks, a little less than 2 weeks. It's a weird format. We do this for a reason. I think one of the big tensions in classes that have big final projects is whether to do a big final project and a big final exam, which I think is a lot for students to do both on. And otherwise, why go to class after the midterm? How do we make sure that there's a reason to learn about the material in the second half of the course, which we do think is valuable, and particularly is often covering more important recent topics, but without doing a really high stakes, large exam. So I talked to a number of people in the sort of the teaching center here called VPTL. And the idea that we came up with is to do a low stakes quiz. And the idea is that it's fun. And I have heard from multiple people that this is actually true. That's the design of it. The design is it's going to be a 2-part quiz. It's multiple choice. It's all supposed to be about sort of high-level conceptual questions. We'll release last year's so you guys can see an example. And so the idea is you do it in 2 parts. You first do it individually. That takes around 45 minutes. And then you'll be paired up with random groups, and you will have to do one joint quiz. And your grade will be composed both of your individual part and your group part, but you can only do better on your group part. So if your group does worse, then you're going to just get the same as your individual grade. So the reason that we do this is that for the group, then it's a scratch-off exam. So you scratch off answers as you decide on them as a group. And the point is that you should be able to articulate why you believe some of these answers are true or false and convince your classmates. And in doing so, that can be a really useful way to think about really knowing the material well and also hearing the perspectives of other people. So that's how the last quiz goes. Again, last year, there was some concern about it before on Piazza. People were concerned. There are certain game theoretic aspects that can come up. We carefully designed this so that it's a very small part of your grade. Again, you can only do better with the group than you can on your individual. So it's carefully constructed. And empirically, when we did this, there was lots of laughter and lots of people seem to really enjoy this aspect. And we've thought about whether we'll do it in multiple parts of the class. But it's different. Almost nobody has ever done an exam like this. So does anybody have any questions about that? It's about 5% of your grade. Yeah.
I remember you saying something earlier on the course that you guys have already decided the teams or will have decided the teams. Is that true?
Yeah, so we haven't already decided that. The question was how are the teams assigned and have we already decided them? We'll do that by random assignment. It'll depend also on which SCPD students are taking the exam on campus or not, but we will release this a few days before, and you'll be randomly allocated to a team, and then you'll just sit with that team for that part of the exam. May you have any other questions about that? And we'll release the sample one. It will cover all of the course. So it'll be more heavily weighted to stuff that's happened since the midterm, but anything from the whole course will be game. And the idea is that someone who has been attending lectures or watching lectures online should have to study for, on the order of a few hours and then be pretty well prepared for the exam. You'll also be able to bring a cheat sheet, just like what you did for the midterm. Are there any other questions about that? Yeah.
And I feel like you probably mentioned this, but I'm just missing which part of the quiz is individual versus with other people. Do we sit down individually and then after like 20 minutes go meet with other people?
Yes. So question is a good one. So what is this individual group thing? So the idea is that you come in, everybody gets an exam, you work on that exam probably from around 45 minutes. You hand it in when you're done. Then when that part of the class is done, most people finish early, it depends, then you as a group get a new exam. And you do exactly the same exam as before, but you just have to jointly agree on the answers. And you scratch it off. So we can see how many you had to scratch off until you got the right answer. But essentially we can just see whether or not you got the answer on the first time or it took more than one. Any other questions about the quiz? If you have any concerns about that, just write, email us on Piazza. I'll just say briefly there about what was one of the concerns that came up last year. The concern was game theory. So you always get the max of your score versus the group score. So what people said is, well, what you should do is you should answer the best you can on your individual part because that's worth the most credits. And then on the group part, you should, if you were torn between two, you should get people to agree on the second answer to hedge your bets. You can do that if you want to, or try to, or your group members can outweigh you. Again, the group part last year was about 0.5%, so it's very small. So there is that possibility. You would only want to do that if you were genuinely really torn between two options. And again, there's only one right answer. So I think that we observed in practice there was very little need to do game theoretic analysis of this. But again, we're always welcome to hear how people interpret these things. All right, any other questions about the quiz or logistics right now? We also, most of you who have already turned in your milestone for the project, we'll be giving feedback on those over the next few days for those of you that are not doing the default. Okay. All right, so I put this up before. This is for everybody that didn't see it before. The grade distribution is basically identical. So today we're going to do the last part on fast learning. This is a really big topic. There's tons of work on it. We'll spend some more time on it today, and then on Monday, Chelsea Finn, who's just finished up her PhD at Berkeley, and she'll be joining faculty here in the summer, will come and talk about meta-learning, which is also a really exciting area, and she'll be talking about meta-learning for reinforcement learning, where meta-learning is relevant to sort of multitask or transfer learning tasks. So just to go refresh our minds about what we're talking about in terms of this fast learning, we're thinking about cases where data matters. So things like healthcare and education and customers. I was giving an invited talk at Pinterest on Monday. They definitely care about these types of ideas as well. And we've been talking about two different settings, bandits and Markov decision processes, as well as frameworks for formally understanding whether an algorithm is good or whether it is fast in terms of the amount of data it needs. And I'll note there that we haven't talked much about computational complexity for this part of the course, but there are similar, some of these frameworks can easily be extended to talk about polynomial sample complexity. So often you can extend these frameworks to also account for computational complexity requirements. Okay, so let's continue with Markov decision processes. What we started seeing last time is that we've built up sort of this expertise on bandits so far of thinking of a couple of the main ways we evaluate whether or not a bandit algorithm is good and approaches to try to achieve that. So we talked about mathematical regret, which was the difference between how well we could have acted and how well we did act in bandits. And a lot of the work in bandits focuses on regret. We also talked about two different types of techniques for trying to achieve low regret, which was optimism under uncertainty, and then also Thompson sampling. So trying to be Bayesian and explicitly represent posterior over what you think might happen when you pull an arm or take an action, and using that sort of information. Then last time we started talking about Markov decision processes, where I argued that very similar ideas are important here, but the problem is a lot more challenging in many ways. And we were talking a little bit about probably approximately correct. So in particular, we were talking a bit about model-based interval estimation, which I mentioned was a probably approximately correct algorithm. And so just to remind ourselves, what did PAC mean? And some of you have seen this probably in machine learning. So a probably approximately correct probably approximately correct RL algorithm is one that, given an input epsilon and delta, so epsilon is going to specify sort of how good, close to optimal we want to be, and delta is going to specify with what probability we're going to want this to occur. With input epsilon and delta on all but n steps, our algorithm will select an action where the Q value of that action, the true optimal Q value, is greater than or equal to, I'll write down it as V, the best possible you could have for that state, minus epsilon, with probability at least 1 minus delta. And throughout today, I'm going to be a little bit loose about constants. Sometimes this will be 1 minus 2 delta. Sometimes there might be a little constant in front of here. Sometimes there might be a little constant in front of there. I'll put 1 here just so you keep that in mind. There might be small constants there. Those are just, they might be 2 or 4. But the important thing is that you're very close to optimal, except for maybe a constant factor away, where n is a polynomial function of S, size of your state space, size of your action space, gamma, epsilon, delta. Yeah?
1 over epsilon, 1 over delta.
1 over epsilon. Yes, great. So the question was good is, are these going to depend on epsilon or delta, or 1 over epsilon or 1 over delta? Yes, inside of all the expressions, they'll end up being 1 over epsilon and 1 over delta. So you could equally write this as this. Because essentially, n is going to be larger if you want to be more accurate. So that's going to, as epsilon gets smaller, you're going to need more data to be more accurate. And if you want to be more sure you're going to be accurate, you're going to also scale up with that delta. Okay. And I just want to, before we kind of continue further, I'd like to briefly contrast this with regret, because in the bandit setting, we mostly think about regret. But it's nice to think about what the difference is between PAC and regret, particularly in online learning, meaning like our algorithm's learning online in an MDP and it's learning forever, which is what regret is telling you. So regret is saying, is that large enough in the back? Can you see regret? Okay, so what regret is saying is, let's say we start off at a state S0. Regret is saying, what if you did the optimal thing from then onwards? And like, how great would your life have been? So if you had won that, first coloring contest, then that set you up for Harvard and it set you up for the Supreme Court, like, it's fabulous. But if instead you didn't enter that coloring contest and you got down here instead, so you could have had like a plus 10 there, but instead you had a 0, and you went to a different state, or you went to a different state in terms of an MDP, where now you are not the person that won the coloring contest. And so then, your life trajectory was irreversibly ruined. In this case, you are judged with respect to not just the actions, but the state distribution you could have got to under the optimal policy. So you're always being judged with what could I have reached if from the very beginning I always made optimal decisions. I always went into that coloring contest. I always went to Harvard. You know, I never went to that Stanford place, and you got up to the Supreme Court versus as soon as you make a different decision, you might end up in a different state's distribution, but you're going to look at these gaps. Okay. So you're going to be judged by the state distribution you ended up in and the rewards you got there versus the state distribution you'd get in under the optimal policy and the rewards you'd get there. So regret in some ways is a pretty harsh criteria because it's saying like you always have to be judged for like if you'd made optimal decisions forever. PAC is much more reasonable in certain ways. PAC says, I'm judging you under the state distribution you get to under your algorithm. So, because it says it'll take an action that's close to optimal for the state that you're in. So what does PAC say? PAC says, okay, you started off here, you didn't enter the coloring contest, you went to there. Okay, that's too bad. Given that, you could have then, you know, I don't know, entered the next coloring contest, or you didn't, and I'm going to be judged by that local gap. I'm going to always only be judged by how optimal am I given the distribution of states I'm getting to under my algorithm. So PAC can have much smaller regret, or sorry, much smaller sort of negative differences compared to regret. Because imagine you have a really harsh MDP and you have to make the first right move and then you go to some wonderful land, else you always toil about in this horrible grid world. So in that case, regret would compare you to if you'd actually made the right first choice, whereas PAC would say, okay, maybe you made a bad first choice, but like you're making the best of things for where you're at, and you're kind of being near optimal given this bad state space you've ended up in. So in some ways, you can think of PAC as kind of making the most of the circumstances you've got yourself into, whereas regret is always judging you from if you'd made good decisions from the beginning. I saw a question back there. Yeah, and everyone, please remind me of your names. I know I'm trying hard, but I sometimes forget. Yeah.
Episodic MDPs?
Great question. The question is, does this extend to episodic MDPs? So in episodic MDPs, just to recall, those are MDPs where we act for 8 steps or a finite number of steps and then we reset. In episodic MDPs, regret and PAC are closer because normally the PAC guarantees we get in that case, I'm not going to talk too much about those today, but are going to be with respect to the starting state. So you're going to look at like V star of S0 versus Q star of S0 of like the actions you're taking or the policy you're following. So in those cases, they start to be closer because you're always being judged from the starting state and you can reset. But in online, like continual learning for reinforcement learning, they can be quite different because the state distributions can be so different. Yeah.
Could you just explain one more time where C1 and C2 come from? Because I don't see them as any like given parameters.
Oh yes, I just put questions about C1 and C2. I'm going to be very loose with constants today. Most of these type of regret guarantees are all about orders of magnitude. So it's stuff like, is n a function of s to the 6th, or is it a function of s to the 4? And we generally don't worry about constants too much. So I just put these in there to say some of the different theoretical bounds will have different constants there. But for today, we're just going to kind of ignore those, but just so that you know that there might be constants there. This might be 1 minus 2 delta, for example, instead of 1 minus delta. Okay. All right, so that's one of the differences between regret and PAC. So let's go back to this algorithm now. And I'll highlight, so we'll talk a little bit about generalization later today, but I wanted to go through sort of how do we start to think about whether an algorithm is PAC or not. I told you that this algorithm is PAC, but I want to talk some about why it's PAC and what it means for an algorithm to be PAC. And are there general sorts of templates that we can use to show an algorithm is PAC? All the stuff I'm going to talk about right now involves tabular settings, where we can write down the value function as a table. And later we'll talk some about how these ideas extend. We're particularly picking this algorithm, which is what's known as a reward bonus algorithm. So we have this nice little reward bonus here, because it's going to be easier to extend to the model-free case. Now, one thing I just want to highlight when we look at the MBIAB is that if we go back and refresh our memories about this, what we were doing is we were computing the maximum likelihood estimate, or otherwise known as just adding up the counts and dividing, of the empirical estimate of the transition model and the reward model for every state action pair. So we look at how many times we've been in a state action pair, which next states we transition to, and we use that to construct an empirical model. And we do the same for the reward structure. And then when we want to figure out how to act, we take those empirical models, and you can think of this operator here as if we're slightly changing our reward model. So I put it here as the empirical reward plus this bonus, but you can alternatively think of this as like an r hat prime, which is equal to r hat of SA plus this bonus term. So you can think of this as like kind of defining a new MDP. There's a new MDP where the transition model is t hat, and the reward model is r hat prime, which is the empirical reward plus this bonus term. And it's not a real MDP, but that's an MDP we could solve and try to compute the optimal value for, and that's what we're doing here, is we construct this sort of optimistic MDP where we're using the empirical transition model, and then we use a reward model that has really large bonuses in places we haven't visited very much. All right, and a key thing we're going to see shortly is the critical thing is how optimistic to be. And there's been tons of work on trying to make things more or less optimistic. And if we have time, I'll show you some other slides about sort of recent progress in this field. Okay, so we talked before about this being PAC, and then now let's talk a little bit about sort of what are the sufficient conditions to make something PAC, and then how does MBI-EB satisfy those form of conditions. So the conditions that I'm going to talk about are derived basically from this paper, with slight modifications. That paper does not, I'll just write down here, does not analyze MBI-EB. So things would have to be a little bit different, but from a 30,000-foot perspective, this is basically a reasonable way to think about why MBI-EB is a PAC algorithm. Okay. So let's unplug this, or yeah, let's unplug this and do this on the board because I think it's helpful to kind of see all of it at once. Okay, so what is a sufficient set of conditions to make something PAC? I know that I found this paper super helpful when I was starting to do PAC proofs in my PhD. So what's a sufficient conditions for PAC? And the theory is beautiful, but even for those of you that aren't interested in the theory, I think looking at this is helpful because it gives one an intuition about what types of properties your algorithms need to have in order to be efficient, or what types of properties are sufficient for your algorithm to be efficient. Okay, so the first one is optimism. Again, this is not the only set of conditions that are sufficient for something to be PAC, but here's a set. So here's optimism. Okay, and optimism simply says that the computed value you use, okay, so this is ST, this is AT. So this is the actual value we compute, like from MBI-EB, that optimistic value we compute. So this is the computed value of your algorithm. Has to be greater than or equal to the true optimal value for that state action pair minus epsilon on all time steps. So it says that whenever we're doing that MBI-EB calculation, when we take in our empirical models and we add in that reward bonus, we have to pick a reward bonus so that whatever we compute for the resulting state action pair is optimistic, minus some epsilon on all time steps. All of this is only going to need to hold with high probability, but I'll just write it out like this. So this is the first condition. The second condition is a little bit more subtle, but I'll say more in a second about the specific cases for this. So the second thing is what's known as accuracy. I'll write down accuracy first. So the first thing says you need to be optimistic on all time steps. The second thing says you need to be accurate. which means that VT, this is again what the algorithm computes. Your algorithm is going to compute this. This is what MBI computes using your optimistic model. Needs to be minus V pi t of a weird MDP. I'm going to tell you about that weird MDP in a second. It is not the MDP I just said that is the nice optimistic MDP. It is not the real MDP. It is an MDP that's sort of in the middle of those. And this type of trick in RL comes up a lot, where we sort of construct, you've seen probably in several proofs now where we add and subtract the same term, which is sort of halfway in between, say, two different Markov decision processes. We're going to play a similar trick here, and we're going to construct an MDP that is sort of half optimistic and is half like the real MDP. Again, this doesn't exist in the real world. We're just going to use it as a tool for our analysis. So I'll say what this is shortly, or what, there's different ways to define this, but it says that something that's going to be closely related to both your optimistic MDP and the true MDP, that your value, so this is, pi t is the policy you're actually executing at time step t, that the value you compute has to be close to this sort of weird hybrid MDP within epsilon. So it has to be pretty close to this other MDP. And the reason for this is that we're going to be able to use this to try to bound how far away we can be from the real MDP. So why are we going to need this? We're going to need this because optimism would be easy to hold by just setting our values super high and never updating. So that's fine, but you need to be able to use the information you have so that eventually you're going to be acting near optimally. So if something really is bad, you don't want to be really optimistic forever. And so the accuracy condition is going to say, if we've got sort of enough information about some state action pairs, our value for some of those needs to be fairly close to a real value. Okay. And then the third thing is bounded learning complexity. Okay, so 3. This has two parts. This says the total number of updates, total number of Q updates. So in MBIEB, we would update our state action values, and we would rerun that sort of optimistic Q value iteration. The total number of times we do that is going to be bounded, as is the number of times we visit an unknown pair, state action pair. And I'll say more what that is in a second. Okay. So we're going to classify all state action pairs. And we're in the tabular setting, so this is reasonable for us to do. We're going to end up classifying every single state action pair into being either known or unknown. And we're going to say the total number of times we visit an unknown state action pair. Both of these have to be bounded by some function. It is a function of epsilon and delta. So it means you can't do an infinite number of Q updates, and you can't visit unknown state action pairs an infinite number of times. Like your algorithm can't. These are conditions on your algorithm. Okay. So if you can satisfy all of these, then your algorithm is PAC. So if 1 through 3 are satisfied, then you'll be order epsilon optimal. On all but, and I'll write this out here just so you can kind of get a sense of what these type of bounds can look like, on all but n, which is equal to order this sort of bounded sample complexity divided by epsilon times 1 minus gamma squared times some log terms. So essentially this is saying that if you can be optimistic, accurate with respect to some weird MDP I haven't told you about, and that if your total number of Q updates and the number of times you visit unknown state action pairs, which I often haven't told you about exactly how we're define that, if that is bounded, then you're going to be PAC. You're going to be near optimal on all time steps, except for a number that scales as a function of this, which is also generally a function of the size of the state space and action space. This is also a function of, say, and epsilon of 1 minus delta. So this is kind of a template. So if you can show that your algorithm satisfies these properties, then you can show that it's PEG. Oh. All right. So how does MVI-EB satisfy these properties? Well, the first thing we need to show is that MVI-EB is optimistic. Yeah, question.
So the first question was like for part 1 and part 2, do they both have the same bounds, or are they just two separate bounds of like different magnitudes?
Good question. I'm asking about, do you mean the epsilon there?
The total number of Q updates and the number of times you visit other states.
Good question. So for part 3, as the total number of Q updates and the number of times we visit state action pairs, they are going to be very closely related. Essentially, whenever you visit an unknown state action pair, then you can do a Q update.
For part 1 and 2, do the epsilons going to be the same?
Yes.
Or-
Yeah, good question. So that's what I thought you were asking. In 1 and 2, the question was, are epsilon the same? Yes, they're the same. Epsilon is same through 1, 2, and 3. So if you're designing your algorithm, 1 and 2 and 3 all have to be the same. Constants probably don't matter. It can, be 1 minus. In some of these cases, you can have a constant in front of the epsilon. One just has to be a bit careful. So for here, we'll just put them like that. Okay, same epsilon everywhere. Okay, so let's talk first about why MVI-EB is optimistic. Actually, can we put this up, please? I think that'll be better. So I'm going to just re-put up MVIE's bonus term so that you can see what that looked like. Okay, so I think this is going to go up in just a second. And then just remind us what the update was for QLIT. So in what we were doing in MVI-EB is we had a state action pair. We had our empirical reward for that state action pair, plus our bonus, beta divided by square root of NSA. Is that too small in the back, or is that okay? It's okay? Okay, great. I see at least one person nodding. So this is our sort of optimistic reward. You can call this like R tilde. This is our optimistic reward. Plus sum over S prime. This is our, again, empirical transition model, S prime given S A, max over A prime of Q tilde of S prime A prime. Okay, so this would be a backup we could do. So it's like a Bellman backup with our optimistic reward bonus. And just to remind ourselves, beta was going to be defined as 1 over 1 minus gamma, square root of 1/2 log 2SAM divided by delta. All right. So in this case, what we want to be able to show, we don't have to think about known or unknown state action pairs yet. We want to show that this value, when we compute it, is an upper bound to the true Q star, up to epsilon. So we want to be able to show this first optimism condition. What we're trying to argue right now is that that beta is sufficiently large as a bonus that when we do this procedure, we're going to be optimistic. Okay. So let's step through that here. Okay. So how do we show that? Let's think about a particular state action pair. So let's think about one state action pair, so SA. And let's think about that we visit it some NSA times, which is less than M. Okay. So in our algorithm, we are only going to update our empirical estimates until we have M samples. So we only use the first M samples of SA to compute R hat and T. Okay. After that, we're going to throw away our data. So this is like saying the first M times you visit this particular state action pair, you can use that data to try to compute an empirical model. You can use it to compute an empirical model before you have M counts. But after that, you're never going to update. I'll just put a side note in there, which is you might think, why? Why should we do this? And in particular, there's a really lovely description of the whole field of machine learning by Tom Mitchell, who's one of the founders of machine learning, where he argues the whole discipline of machine learning, the point is to look at the foundations of how an agent can learn, and also that we design algorithms that continue to improve with more data. And this is violating that to some extent, because this is saying that even if you get 10 trillion examples of that state action pair, which surely would make your empirical model better, we're going to throw all that data out. Just to give you a sense of why we do that, or why this earlier analysis did that, we do that for the high probability bound. The idea is that the high probability bound is going to work like what we saw for bandits, of making sort of upper confidence bounds and kind of guaranteeing that our estimates, say of the transition model, are close to the true values. And those bounds all hold with high probability. And so who here has seen union bounds in different things? Okay, a few people, but most people not. So union bounds are a way to make sure that if you have a number of different events, all of which hold with high probability, that the total of those events all hold with high probability. And that is essentially why here we only use a finite amount of data. Intellectually, this is completely unsatisfying because you should clearly be able to use more data, and your algorithms should do better with using more data. And empirically, we use all the data. One thing that I find really satisfying for the last few years is that for Lattimore, who's one of the authors of the Bandit book that we recommend, we showed that you can remove this restriction. You can just continue to use data forever by using smarter things than union bounds. But regardless, for today, we're do this. So we're gonna say we're only gonna use up to m samples, and let's think about cases where n of SA is less than or equal to m. Okay, so we have up to m samples, but in general, it might be 1, it might be 2, some number that is smaller than m, which is some constant that we have not specified yet. Okay, so what we're going to look at is for this state action pair, we're going to look at all of the experiences for that state action pair. So let's call xi to be defined to be ri plus gamma v star of si. This should look quite like what the sort of targets that we had in TD learning. This is saying that the reward we got on the ith time we sampled S and A, and the next state we got to on the ith time we sampled S and A. So this is from ith visit to SA. This is the next state. Next state. All right, so we can define this. So you can think of each of these are going to have an expectation of the true Q star of SA. Okay? Because I've just defined this. We don't have to know what V star is right now. We're just analyzing what would happen with these samples. So if we define our samples to be the real reward we saw, the real next state we saw, on average, this is really just Q star of SA. All right, so if this is Q star of SA, we can think about how many samples do we need until we have a good approximation of Q star SA, or how far away can our average be over the real empirical average of xi's versus Q star. And we can do this using Hofting or other sorts of deviation bounds, a little bit like what we saw for bandits. So for bandits, we looked at if you have a distribution over rewards, if you have a finite number of samples of that, how far can it be away from the true mean reward? And similarly here, we're going to say if you have a finite number of samples of the next state and the reward received, how far away can we be from the true Q star in this case? All right, so there's some technical details here because one has to be a little bit careful about the fact that the data that we gather depends on the history. So this is, again, one of the more challenging things in Markov decision processes in the sense, or particularly Markov decision processes, in that the data you gather depends on your algorithm. So you're going to get more samples for state action pairs that you think are going to be good, and less samples for state action pairs that you think you're going to be bad. So there's coupling. The data isn't really IID across the whole distribution, but sometimes conditioned on the fact that we're sampling for the state action pair, the next state and reward are IID because it's Markov. So just to give that's just to say we have to be a little bit careful here, but we can basically use things like Hofting to say the probability that Q star of SA minus 1 over NSA sum over I equals 1 to NSA of xi, where xi's are just what we defined up there. The probability that's greater than or equal to beta over square root of NSA is going to be less than or equal to the exponential minus 2 beta squared, 1 minus gamma squared. Okay. So this is using like Hofting or a similar type of deviation inequality. You can also use ones that depend on martingales, for those of you that have seen some of those before. Regardless, this basically just allows us to say, as you get more and more samples for this particular state action pair, how far away could you be from optimal if you did know B star? Now we know what beta is, I put it up there. So if we plug beta into here, so if you plug beta in, the real value for beta in, you get that this is going to be equal to delta divided by 2 size of the state space, size of the action space, m. Okay. So it just says that this holds with high probability. That the number, as you have more samples, the probability that you're going to be far away from the true Q star is small. Okay. All right, so we can put that, like substitute this result back in, and we can say what that therefore means is that if we look at the union bound across all of this, well, here, let me just write down one more thing, which is what does this xi actually look like? So xi, if you say 1 over NSA of sum over I equals 1 to NSA of xi, what is that? That's actually just the equation that we had up there. Okay. So it's very similar to, it's your empirical reward plus gamma times t hat s prime sa, almost that equation, except for you've got B star here. Okay. So this should look really similar to that Q tilde up there. We're using the empirical rewards here in the empirical transition. The difference is that here we're using Q star, and up there we're using Q tilde. Okay. All right, so what this means is that if you have a number of samples, then you can bound the difference between the thing that we're doing up, this thing, and the Q star. So let's do r hat of SA plus gamma sum over S prime transition, the empirical transition model, SA V star of S prime minus Q star of SA is greater than or equal to minus beta divided by square root NSA. Okay. And this is going to hold for all T, S, and A. Right, so we've used Hofting, and now we can relate the empirical reward, the empirical transition model, and if someone gave us the optimal Q, to what Q star is. And then now what we want to do is compare this to what that equation up here. So I'll just, right, this is 1. So that equation 1 up there is what we're actually doing in MBIEB. We keep doing that over and over again until it converges. So we take our empirical transition model, we take our empirical reward model, we add in this bonus, and we do value iteration until we converge. And what we would like to do now is to compare what happens to that quantity versus what is Q star. Okay. And we want to show that that quantity up there is going to be greater than or equal to Q star. Okay. So we're going to do that by induction. I think I'm going to, let's see. So the proof is by induction. So what we're going to do is we're going to get Q tilde I of SA be the ith iteration of value iteration. So this is using that equation 1. So equation 1 up there. And we're going to let V tilde of I equal for a value S just to be if we were to take the max action of that Q tilde. Okay, for every state and action pair. And what we're going to assume is that we initialize optimistically, and we're going to initialize Q tilde of 0 for SA equal to 1 over 1 minus gamma, which by definition is greater than Q star, is at least as good as Q star. So that's our base case. Again, what are we trying to do? We're trying to show optimism here for MBIEB. We're trying to say that if we do this procedure with MBIEB, we'll be optimistic. We're going to do a proof by induction, and this is the base case. So we start off, we initialize our Q tilde optimistically. And now we're going to assume that this holds. So we're going to assume Q tilde I of SA is we're going to assume that Q tilde I of SA is greater than or equal to Q star of SA for the previous time step. Okay, so we're going to all right, so let's write out what QI plus 1 is going to be. Q tilde I plus 1 is going to be equal to, for SA, is going to be equal to our empirical reward plus gamma sum over S prime, our empirical transition model, times our V tilde of I of S prime plus beta over square root NSA. Okay. That's just the same as equation 1. So now we're going to say that this, by definition, is going to be greater than or equal to R hat of SA plus gamma sum over S prime, our empirical transition model, times the true V star. Okay. Because that's our inductive hypothesis. We assume that this held on the previous time point. Okay. Plus beta divided by square root NSA. This is by inductive hypothesis. We assume that we have a base case where this holds. We're going to assume that that held on the previous iteration. And then the last part that we need in here is that this part, we look at this part versus this part, okay? So if you rearrange this equation, then you can see that R hat of SA plus all this stuff is greater than or equal to Q star of SA plus minus beta square root and SA. Okay. So that means that if we substitute that back in over here, we can say this is equal to Q star of SA minus beta over square root NSA plus beta square root NSA, which is equal to Q star. Okay. So now we've shown optimism. So the key ideas in that case was to say, we know that we're going to relate this to what would happen if we had the true Q star. We'd show that if we know the true Q star on the next time step, then doing this one step back up, we can bound how far away we'd be from Q star in terms of our function beta. And then we can do an inductive proof to show that if we were optimistic on the previous time step, we can always ensure that held at the beginning because we used optimistic initialization. Then we'll continue to be optimistic for the resulting Q star. So this proves optimism. Maybe any questions about that proof? Okay. So that's the proof of optimism. The other key part, and I won't go through the other part in quite as much detail, but I'll talk about it briefly at a high level. The other really important part is accuracy. I mean, bounded, I'll keep this up in case anyone's still writing. Accuracy is really important. And the fact that you will eventually become accurate is important. So the intuition for this part is that you can think of defining a couple different, well, you can think of defining things as being known or unknown. Somebody want me to keep this up, or is everyone finished writing? Raise your hand if you'd like it up. Okay. Okay. So in many PAC proofs for finite state and action pairs, there's this notion of knownness. So what does it mean? So known state action pairs. Intuitively, known state action pairs are going to be pairs for which we have sufficient data that their estimated models are close to the true model. So the intuition here, SA, where R hat of SA and T hat of SA, S prime given SA, are close to true RSA and TSA. So intuitively, if you get more and more data for a particular state action pair, we know from Hofting, et cetera, that your estimated mean is going to converge to the true mean, and your transition model is also going to converge to the true transition model. And what we're doing here is we're sort of drawing a line in the sand, and we're saying, when do we have enough data for a state action pair that we are satisfied with our empirical estimates, where we can bound how close our empirical estimates are to the true models. And if things are close enough, then we know that using those allow us to compute a near optimal policy. So if everything is known, if all SA pairs are known, then we can show that the V of pi star under your sort of empirical model, I'll denote that as hat, so this is like your empirical model, minus V pi star, and I'll put this under your empirical model, V of your true model, that this is bounded. Not going to go through all the details so that you saw a little bit of this on the midterm. This is often known as the simulation lemma. If things are close, like if your models are close, your transition model is close to the true transition model and your reward models are close to the true reward model, then if you use those to compute a value function, your value functions are also close, which is a really cool idea. It's basically saying you can propagate the errors in your empirical model into the errors that you get in your value functions and the errors you get in your policies. So you can sort of propagate error. You can go propagate empirical predictive error to control error. Bless you. Bless you. So this is this really nice idea. You can say, like, if you have good predictive error, then you can end up with small control error. And the known state action pairs are just providing a way to sort of quantify whether, what level do you need in order to be good enough. And the good enough you need is going to depend on what that epsilon is you want. So one really important idea is to think about these known state action pairs and what they allow us to do in terms of defining some alternative MDPs. So in this case, I'll erase this. Just so you know how sort of some of the parts of the proof would go forward. I won't go through all of it in detail, but I'm very happy to talk about it offline. Is we can define two other sorts of MDPs. We can call an MDP M prime, which is a MDP where for SA pair, it's R and T, so its transition and its reward dynamic, its dynamics and its reward model are equal to the true MDP on SA in known set, else it's equal to the M tilde model. So these are where we sort of start to define these slightly weird MDPs. So this is a model that is not quite our M tilde model that we're using to do in that equation 1, which we have these kind of like rewards plus bonuses plus our empirical transition model. And it's not quite the real model. It's saying on things that are known, we're going to use the real world model. Again, we don't know what any of these are. These are just tools for analysis. And then on state action pairs, which are unknown, we're going to use this optimistic model. This defines an MDP. And the reason that this is useful is we can end up using it to help figure out how does the MDP that we have relate to the real MDP on state action pairs that are known. Okay. So this is one MDP we end up using for this. And then the other one is a similar one, which is M hat prime, which is an MDP equal to M hat. So this is just the empirical estimates on K and equal to M tilde on all others. So on the known set. Okay. So this is an MDP where for the known set we use our empirical estimates, not the true models, and then we use M tilde on all of these other ones. So the idea is that we can use these different forms of MDPs and we can quantify how far off the value is that we get by computing using our Q tilde versus the value on these other ones, and we can use it to basically do a series of inequalities to relate the value we get by executing our policy versus the value we get in the true world under the optimal policy. So these are the types of tools that allow us to help prove accuracy on state action pairs that we know about. Yeah?
Sorry, is that M hat and then M tilde?
Yes.
What
This is
are
M hat. So M hat here is the empirical estimates, like the, if you use just the counts of the rewards and the counts of the transition model. M tilde is the empirical estimates plus the bonus. Yeah. So the transition model in these two cases would be identical, but this one would have the reward bonus term. Okay. So intuitively, this allows us to help quantify the accuracy. The final thing that I guess I just want to mention briefly of how these types of proofs tend to work is that we need this bounded learning complexity. We need to make sure that we're not going to continuously update our Q function. We're not going to continuously run into unknown state action pairs. So the last part is to sort of, how would we prove 3, which is bounded learning complexity? And the intuition for this is a little bit like the general intuition for optimism. So the intuition for optimism was to say, if you assume the world is awesome, either the world is awesome, in which case you have low regret. In the case of PAC, that means if you assume the world is awesome and it really is awesome, that's like not making a mistake. That's like picking the action that you pick is good. So then you won't suffer a worse than epsilon decision. And then we want to be able to say that the times where you don't make mistakes, or where you do make mistakes, where you pick an action that's bad, which is less than epsilon close, is bounded. And that's what this is about. And the key idea here is the pigeonhole principle. So the idea is that if you think about, you don't have to have episodic MDPs, but if you have, you can think of dividing your stream of experience into episodes. And during each sort of episode, you can think about whether it's likely that you're going to run into an unknown state action pair. So you consider, what's the probability that we reach an unknown state action pair? Remember, an unknown state action pair here is one that we don't have good models of. Like we've only visited it once or something. So what's the probability we're going to reach an unknown state action pair in t steps? So what we can show in this case is that if this is low, if this is small, if that probability is small, we're being near accurate. We're being near optimal. So if it's a really small probability that you're going to reach anything that's unknown, we can show that on the known state action pairs, you're being near optimal. So if you're unlikely to reach anything where you have bad models of it, you're going to be near optimal. If it's large, this can't happen too many times. So if it's large, you're going to visit it. It can't happen too many times. Because if this is large, that means that you're really likely to reach an unknown state action pair. Remember, I said that for every state action pair, you only update it at most m times. So by the pigeonhole principle, this probability cannot stay high for too long. Essentially, you're going to have a function of like the number of states, the number of actions, and m. It's larger than that, but this is saying that you need to be able to visit each state action pair m times. So that goes into our end bound here of the times we're going to make mistakes. And we might sort of reach things that are unknown. It might take us more steps and we might make some bad decisions along the way. But essentially, things can only be unknown for m steps for each state action pair, which means that our probability here has to be bounded. So eventually everything has to be known or you have to be acting near optimally. And that allows us to show that things have that things are pack. It has bounded, we're going to make a bounded number of bad decisions. So either we're not going to be reaching any part of the state action space which is unknown, so everything we reach, we have good models of them and we're using them to make good decisions, or we are reaching things and then in that case we're getting information because we're getting a new observation of what it's like to be in that state action pair, and something can only continue to be unknown until we get m counts. Okay, do you mind putting down the thing again? Okay, so that gives us an overview of why MBIEB is pack, as well as sort of why a lot of the types of proofs that you do to show things are pack. And I think the key ideas in this is really this sort of notion of optimism and accuracy and the ability to make progress, the ability not to be stuck always wandering by decreasing these confidence intervals sufficiently fast. Okay, so now let's go back to Bayesianness. So that kind of concludes the pack MDP part for a while. There's been a lot of exciting recent work in this area. I guess let me see if I can just really quickly bring this up. This is from a presentation one of the CAs is giving up at Berkeley today on some of our joint work together. Just to highlight here, in terms of sort of pack and regret analysis, there's been a lot of progress on getting better approaches. So over the last few years, me and some of my grad students, some other really nice groups have been doing a lot of work on this. And we're also now trying to have analysis that is problem dependent, which means that if the algorithm has more structure, then we should need less data in order to learn to make good decisions. So now let's be Bayesian and see how being Bayesian helps us. So we saw Bayesian bandits, and in Bayesian bandits we said we're going to assume that we have some parametric knowledge about how the rewards are distributed. So we're going to think about there being a posterior distribution over rewards, and we're going to use that to guide exploration. And we particularly talked about this notion of probability matching, which is we want to select actions with the probability that they're optimal, and it turns out that Thompson sampling allowed us to do that. So in these sort of approaches, it was very helpful if we have conjugate priors, which allowed us to analytically compute the posterior over the rewards of an arm, given the data we've observed, and our previous prior over the probability of different rewards for that arm. So we saw as one example of that the Bernoulli, which means that the reward is just 0, 1, and the beta distribution. And the beta distribution is one where we can think of the alphas as being counts of the number of times we've seen a +1, and betas is the number of times we've seen the arm being 0. And as we get observations of one or of either of those outcomes, then we just update our beta distribution. So that allowed us to define Thompson sampling for bandits, which was this algorithm where we say at each time step, we first sample a particular reward for each of the different arms, and then we could sample a reward distribution, we compute the expectation for those reward distributions, and we act accordingly. So we saw this for the toe example, where we saw that we would sample different rewards and then use these to act. And at least in that example, we were seeing that we happened to exploit much faster than what we were seeing with an upper confidence bound approach. So a very similar thing can be done in the case of MDPs. So now in being Bayesian for models-based RL, we're going to have a distribution over MDP models. So what's the difference here? That means we're going to have both transitions and rewards. So we're going to have the rewards should look very similar to bandits. So the rewards, very similar to bandits. You can also use betas. If your reward distribution is 0, 1, you could also use betas and Bernoullis. So this is very similar to bandits. T is a bit different. We're not going to talk a lot about the different distributions you can use, but for example, if we're in tabular domains, T can be a multinomial. And the conjugate prior for multinomial is a Dirichlet. It's conjugate. So if you want your transition models to be a multinomial, which is the probability over all the other states and actions, then a conjugate prior for that is a Dirichlet, which has a very nice intuitive description similar to what beta is. In beta, you could think of this as just being the number of times you've observed 1 or 0. If you look at a Dirichlet, you can think of this as being the number of times you've reached each of the next states. So S1, S2, S3, S4. So the Dirichlet distribution would be parameterized by a vector for one of each of the states. And again, we can use this sort of posterior to update it to allow us to do exploration. So in this case, we're going to sample an MDP from the posterior and then solve it. So if we look at what the algorithm looks like, it's going to look very similar to Thompson sampling for bandits, except for now we're going to start off and we have to define a prior over the dynamics and reward model for every single state action pair. So notice this is tabular. We're assuming that we have a finite set of S and A. So we can write this down. We can write down we have one distribution for every single state action pair for both the dynamics and the reward model. And then what happens is that you sample an MDP from these distributions. So for every single state action pair, you sample a dynamics model and a reward model. And now you have an MDP. And so once you have that MDP, you compute the optimal value for it. So this is obviously more computationally intensive than what we had for bandits, but it's certainly a reasonable thing to do. And then you act optimally with respect to the Q star you have for that sampled MDP. So this is known as Thompson sampling for MDPs. It also implements probability matching. And empirically, it can often do really well, just like Thompson sampling did really well often for bandits. So I think that's probably all I'll say about Thompson sampling for MDPs. There's been a number of different works on this, just to highlight some people that do some really nice work on this from Stanford. Ben Van Roy's group has done a lot of work on this, and sometimes they call it posterior sampling for MDPs. So people like some of his former students like Dan Rousseau and Ian Osband. Ian's now at DeepMind. Dan Rousseau is now at NYU. They've done some really nice work in these types of spaces. Yeah?
Would you generalize this like non-tabular MDPs?
Yes, great question. So the question was whether or not we can generalize this to non-tabular MDPs. Yes, and I'll talk about that in a second, but kind of poorly. But yes, that's the goal. All right, anybody have any other questions about sort of finite state and action scenarios? Now we're going to talk a little bit about generalization. Okay. All right, so of course, everything I've just been saying right now is for finite state and action spaces, which is not very satisfying. Because if we think about these types of bounds, I said this was polynomial in the size of the state and action space. So what if S is infinite? I mean, it says we could make an infinite number of mistakes, and that seems sort of unfortunate. So it's not clear that this initial framework is at all helpful when your state space is either infinite or insanely large, like the space of pixels. So even though the framing of this is really nice, we would like to be able to take these types of ideas up to generalization, but we'd like to figure out how to use them in a way that can be practical. Now, when we start to, so this is a very active area of current research. There's been a lot of different ideas about this over the last few years. I do want to highlight that on the theory side, we still have a long way to go. As we talked about some with function approximation, even just function approximation and doing control, like off-policy control, like Q-learning, we said that we didn't have good asymptotic guarantees for some of the basic algorithms. So if we don't even have good asymptotic guarantees, it's unlikely that we would have really nice finite, these are often known as finite sample guarantees because they guarantee that the number of mistakes you're going to make is finite. So we have relatively little theory in this case. It's something that my group is working on. There's several other groups that are also working actively on this, but there's a lot still to be done. But there has been some really nice empirical results recently. Okay, so let's think first about generalization and optimism, like optimism under uncertainty, where we're now in a really, really large state space. So let's think about what might need to be modified if everything was extremely large. If we go back to this algorithm, well, first of all, we had these sort of counts that we're keeping track of sort of for every single state action pair, what the counts were. So this isn't going to scale because if you're in a scenario where your state space is pixels, you may never see the same set of pixels again. Does anybody have any ideas of how you might extend this to the deep learning setting? Like what we would like in this case is some way to quantify our uncertainty over sort of states and actions. But we don't want to do it based on like raw counts because then everything will just be one forever. Yeah.
Could you use some form of like bounded VFA?
So the suggestion was whether we could do some form of like a VFA, for example. Yes, we could imagine trying to use some form of some sort of density model or some sort of way to try to either get an estimate of how much related information have we seen, or how many related states have we seen in this area.
Does embeddings help some way, like being able to like convert all of these things into some sort of a small vector space?
Yeah, so suggestion was to use some sort of embedding. Absolutely. So another thing you could do here too is to do some sort of form of compression of the state space. One of the challenges is the right compression of the state space depends on the decisions you want to make. And so generally it will be non-stationary. That's not necessarily bad. You might just want to go back and forth between those. So those sort of ideas are great. In general, we want some way to quantify our uncertainty that is going to have to generalize and say similar nearby states. If we visited that area of the world a lot, then we should have less of a bonus on that in terms of optimism. Okay. So as I said, these sort of counts of SA and SAS prime are not going to be useful if we're only going to encounter things once. Another thing that I want to highlight is the methods that I was talking about before are really model-based. A lot of the work there is model-based. In contrast, a lot less of the things, it's starting to change recently over the last year, but in general, there's been much less work on the model-based approaches for deep learning in terms of RL. And I think that's because the model-free and the policy search techniques have generally been much better, in part because the error that you make in your models accumulates a lot as you do planning. And so I always remember David Silver's first talk about this, or one of his earliest talks about this from I think 2014, where he showed this beautiful sort of model-based simulation, which was horrible for planning. So the errors really have to be very good. The errors have to be very small, and it's not clear that the representation you get by maximizing for predictive loss is always going to be the best for planning. So we'd really like to be able to take the ideas we saw before for things like MBIEB and translate them over to the model-free approach and think about some way to encode uncertainty in the deep neural network setting. So let's think about doing something like Q-learning, like DQ learning. And in this case, so I've been a little loose here. You could, this could be a target. So target could fix this. But think about something like sort of the general Q-learning and Q-target, where we use the max of our current function approximation, or we use the max of our current target function approximation. So one idea inspired from MBIEB would be simply to include a bonus term. So again, this could be, a fixed target. But the idea here is that when you are updating your parameters, just put in a bonus term for that particular state action pair when you're doing your Q-learning update or when you're refitting your weights. Of course, we have to know what that Q bonus would be, but this would help with the planning aspect. So now we're in the model-free environment, model-free setting, and so we could, when we're doing our sort of Q-learning updates, let's insert a bonus term. So that's why I chose MBIEB as the algorithm to show you before, because I think that those sort of reward bonuses are much easier to extend to the model-free case. Now, of course, the question is, what should that reward bonus be? It's got to reflect some sort of uncertainty about the future reward from that state action pair. And there's a lot of different approaches that have been trying to make progress on this. So Mark Bellemere and some of the follow-up papers thought about sort of having a density model, trying to explicitly estimate a density model over the states or state action pairs that you visited. Other people have done sort of hash-based approaches, which is sort of more similar to the embedding in a way, try to hash your state space and then use counts over that hash state space and then update your hash function over time. So that's some of the work that's come out of Berkeley. So there's different ways to quantify this. Another thing I want to highlight here is that these bonus terms are generally computed at the time of visit. When we looked at MBIEB, you could recompute these later. So if you're storing things in your episodic replay buffer, you might want to update those over time. Because those state actions, if you now later sample that reward and next state pair from your replay buffer, you may want to change that bonus term. So there's a number of different subtleties when we try to bring this up to deep learning. But there's been some really encouraging progress. So let me just, so in this case, what we can see is the initial work from Mark Bellemere's group, where we compare on Montezuma's Revenge, which is considered one of the hardest Atari games, sort of the progress of a standard DQN agent that was using eGreedy. There's a number of different rooms in Montezuma's Revenge. In this case, you can see after 50 million frames, it was doing incredibly badly. It had only been through 2 of the rooms. Whereas if you use this sort of exploration bonus, this one did much, much better. So just enormously better by being strategic. Okay. So I think that highlights the empirical significance of doing this sort of strategic exploration. Let's think briefly about Thompson sampling. So in this case, one of the ideas that we did a few years ago is to say you could do Thompson sampling both over your representation and the parameters of your model. What do I mean by that? I mean that if you have a really large state space, you could imagine collapsing your states and doing a dynamic state aggregation and sampling over possible state aggregations as a way to sort of do collapsing your state space. And Thompson sampling can be extended to sampling over representations. So that works well, but it doesn't scale up fully. When you want to really scale up, if you want to be a model free, it's a little bit different than what we saw before, because before we saw model-based approaches, and now we're sort of wanting to sample from a posterior over possible Q stars. And it's not clear how to write that down. I don't think we've made good progress on that, even in the tabular setting. But that's what we're trying to do, people are trying to do for the deep learning setting. And there's been a couple different main approaches. One is, again, sort of from Ian Osband, who was here for his PhD. They did bootstrap DQN. The idea here is that you can use bootstrapping on your samples, and you can build a number of different agents. So now you kind of have C Q values instead of just one Q value, and then you can act optimistically with respect to that set. It's not incredibly effective. It gives you some performance gain. Another thing that we did, someone I was working with before, I was involved with one of the earlier versions of this, and since then they've been continuing to push it forward. The idea here is that you kind of fix your embedding and you do linear regression on top. And that is super simple, but if you do Bayesian linear regression, you get a notion of uncertainty, and that actually gives a lot of performance gains in a lot of cases. So you can sort of have like a really little bit of uncertainty representation on top of a deep neural network. But this is an active area. There's a lot of people thinking about this different type of work. And I think it's going to continue to be a really big area because we still haven't made sufficient progress in how to do exploration plus generalization. So just to summarize, I know we've done quite a lot of theory in this section. The things that you should make sure you're familiar with is to understand what is the tension between exploration and exploitation in RL and why this doesn't arise in other types of settings. You should be able to define these different sorts of criteria for what it means to be a good algorithm in terms of PAC or regret, and be able to map the sort of algorithms that we've discussed in detail in class to these different forms of criteria. So if I say, is this optimism under uncertainty approach, is that good for PAC or regret or both? You should know that it's good for both. So that's the kind of high level that you should be able to understand from the things we've been doing. And just know that there's a lot of really exciting work that's continuing to go in there, including defining new metrics of performance. And next time we'll hear about meta learning. Thanks.